Okay, in this video we're going to start looking at the more complex motion when we have translation and rotation at the same time. So we're going to be studying motions such as the one for this link here, which is going to have both a translation and a rotation. So the study of this is going to be going as follows. So we have link, and this is the easiest body to start with. And it basically, you can consider the important thing is that there are 2 points separated by this vector, and this vector, this distance here never changes. So this segment is going to move from here all the way to here. So A move to here and B move from here to this point. So you can see that there is a vector here that tells you about the displacement of A and a vector here that tells you about the displacement of B. And this happens in a time dt, in a delta time dt. So how can we analyze this motion? Well, the translation part is going to be this one here. So you move from here all the way here, and B moves from here all the way here. And this is what the link would be with the rotation. So this is just a pure translation, and the link would be just here. So now to complete the motion, we have to rotate the link about A. So that'll give you this vector here, which is dr of B relative to A. So the way we are going to write this then is that the total displacement of B, right, drB, is going to be equal to the displacement of A, this vector here, right, plus the rotation part, which is the displacement of B relative to A. So there's going to be a coordinate system attached to A, but that coordinate system never rotates. In this type of analysis, and point A receives the name of base point. So let's see what happens just at E. At A, after the translation, the body is going to rotate about A. So it's going to have some angular velocity, right? So B can be written in terms of a rotation about A. So here is how that happens. So you have a general motion that is decomposed in a translation plus this rotation. So if we take that equation that we have before for the displacements and we divide that by t, we get the velocity. Velocity of B, this point here, is equal to the velocity of A. This is if we didn't have any rotation, plus the rotation of B relative to A. But now we know when we have a pure rotation, we know how to write this, right? That's omega r, or omega cross r. So we can write these terms, the velocity of B relative to A, as, well, that's the derivative, and that is also omega cross RB relative to A. So typically, because these are planar motions and this is 2D motion, omega is going to have just a coordinate in the k direction, in the z direction, and that's going to coincide with an axis of rotation that goes through A. So this is our equation for the velocity of V if we know the motion of A. And so now we can use this equation to find velocities and solve some simple problems where we have linkages and other entities like gears or wheels. So one more point here, if we have wheels, we can use this analysis to study the motion of wheels. We should remember that if there's no slipping, this point here, right, when the wheel is not slipping and there is friction here that causes this point to be at rest instantaneously, then we can write the velocity of this point, B, as the velocity of this point, which is 0, plus omega cross RB relative to A. And omega is just the angular acceleration of the wheel. So that's an equation that could be used to find angular accelerations of wheels and study the motions of wheels. So problems that we are going to have and how we solve them, we can use a scalar approach. We establish an xy coordinate system, and then we look at the velocity vectors, and then we look at the magnitudes and directions of each component, and write scalar equations for each component. Or we can use a vector analysis in which we again have an xy coordinate system. Then we have the velocities and the vector RBA, and then we write this as a vector equation with ij components, and then we can solve that. This is going to give you two equations, one for the x component and one for the y component. This is actually my preferred method to solve this type of problems, and let's go and see one example here. We have this roller that is moving to the right. This point A is moving to the right at 3 meters per second, and you want to find the velocity at B when theta is equal to 30 degrees. So let's see how we attack this problem. So we set a coordinate system, right? XY coordinate system. And then this is our equations, right? So the velocity of this point B here, right, is the velocity of this point A. So this just would be a pure translation. And now we add the rotation of this red vector here, about point A. So let's write this. So B is a vector that has only a j component, it's a -1, so this is here. And then A is a vector, the velocity of A is a vector that has only an x component, value 3, that's here. Omega is a vector that has a component in the k direction, so we are going to write that as omega k. And then we need to write the vector from A to B when theta is 30 degrees. So A is 1.5, so we're going to have a negative x component and a positive y component. So after that, we can write the whole equation in ij components. So this is the velocity of B, velocity of A, and omega cross RB relative to A. And now, so you can see here that we have two equations, one for the x and one for the y component, x and y, and we can solve the two and then find a solution for that. Let's look at another example here, right? So we have a crank, this rotates, and then we want to find the velocity of B at a particular time when this is 12 radians per second, right? So again, we need to write this, but there is a key detail here. This omega is not this omega. These are two different omegas. So this is the angular velocity of AB relative to A. And here, this 12 radians per second, this link here is a pure rotation and rotates at 12 radians per second. We can use that 12 radians per second to find the velocity of A, which is that vector there. And VA is omega cross RA, right? So that's what we're going to do in the next. So this is VA. So this here is a vector from A to B, and then BB would be a vector that goes up there. So we can find VA first. So that's 0.3, which is this distance, times the angular velocity. Is a negative vector because it's moving in that direction. So this is VA. And now we write our equation that we want to solve. BV is equal to VA plus omega AB plus RBA. And then we just write this using ij components. So BB has only a j component positive. BA has a x component only. This is the angular velocity that we don't know, k. Cross, this is a vector here. This is R, B relative to A. So we go ahead and do the cross product there, and we end up with this vector here. And now that gives us two equations, one for the x and one for the y component, that we can solve and find the solutions here.